Hello and welcome to the Spatial Structures Movers and Shakers interview series as we look ahead to the IASS Annual Symposium and Spatial Structures Conference taking place at the University of Surrey in August 2021. My name is Mark Richardson and today I'm joined by Professor SeungDeog Kim, who is an Emeritus Professor at Semyung University and a guest professor at Southeast University in China within the School of Civil Engineering. Professor Kim is currently a member of the advisory board of the IASS and a vice president of the SEWC, the Structural Engineers World Congress. Professor Kim, thank you very much for joining us today.
Thank you, Mr. Mark.
Thank you, Professor Kim. It's a pleasure to have you on our interview series. We begin by talking to our guests about lockdown. How has the period of lockdown been for you in Canada, where you're based?
Yes, first of all, I'm very delighted to be invited as one of your guests in the interview. Thank you. Actually, I was working in Korea and retired last summer. Since then, I was back in Canada home. Here in Canada is also not in a good situation since Christmas, the second lockdown started, but the number of new cases haven't reduced much. Starting off last week, the new measure was enforced, which was to just stay at home. Currently, I'm working at home by online, by doing meetings, lectures, and seminars, all in online. In free time, I just spend my time with my family. I hope the pandemic will end soon and we all return to usual life.
Absolutely, Professor. That's a sentiment shared by, I'm sure, all of our viewers and the wider community. Thank you very much for that answer. We also ask our guests about their career journeys and career paths. Perhaps you could provide us with an overview of your own career journey to date.
Yeah, my research journey was from my master course at Semyung University. At the time, it was about numerical analysis, which was rigid element method, and can be used at tracking collapse procedure in elastoplastic range. And then I went to University of Tokyo for my PhD. The topic was dynamic instability of shear structures, which was the combined topic with three subjects: nonlinear dynamics, instability, and shears. My academic advisor for PhD was Yasuhiko Hangai, who you know for Hangai Prize in IASS. I was influenced a lot by Professor Hangai, who was really bright, intelligent, and brilliant. After PhD, I went to Purdue University in United States and joined with Professor C.T. Sun, who was distinguished in the field of composite material. At the Purdue, I studied about the impact analysis with composite materials, which was very helpful in my research journey. After come back to Korea, I started working at Semyung University. At the time in Semyung, I was a very lucky man because 10 World Cup Stadium for 2002 World Cup project was waiting for me. So most of my research achievements about spatial structures were developed at the time, like membrane structures, tensegrity cable domes, spacer trusses, and so on. After setting about most of the technology of soft and hard structures, my main topic was being changed toward the deployable system. It was helpful for of some advice from Professor Kenichi Kawuchi and Professor Neil Tellerman. So now I'm very interested in more advanced structural system, such as space structure in the universe with transformable system, dynamic instability, and so on.
Thank you very much, Professor. That was a very interesting insight into your career. And of course, you were also chair of the organizing committee of the 2012 ISS Symposium, which was hosted in Korea. Please, could you share with us your experiences of this conference?
Yes, I was very delighted how successful the Seoul IASS Symposium had ended, and appreciate all participants for their supporting. We had several experiences for international conferences, such as APCS, but IASS Symposium was the first time in Korea. The 2012 ISS Symposium had around 350 participants from 31 countries. Obviously, the time to prepare for the conference was very stressful. However, it was all worth it. It was a valuable time for both myself and the people in the field of spatial structures.
Fantastic. Thank you, Professor Kim. Well, we'll now move to the middle section of our interview, which is entitled Your Space, Your Structure. So at this point, I will hand over the presentation to SeungDeog Kim, who will be sharing with us a presentation on spatial structures of his choosing. So over to you, Professor Kim.
Okay, I'm going to introduce my research achievement roughly. Today, I selected two topics about deployable system and dynamic instability. In the deployable system, usually there are two kinds of basic system, scissors system and origami, which is a kind of intelligent adaptive structure, which include structure, mechanism, and control each. So first example is about the deployable dome. I selected the meridian type scissors system as a mock-up tester for deployable dome. So I used the electric cylinder to control the scissors structure, which is attached both joint like this. So let me show you the video. This meridian type dome has 2 meter by 2 meter in span and 0.6 meter in height. So you can see this two cylinder here. So it's moving very smoothly. Okay, next project is about deployable shelter. First, I examined two kinds of model. Model A is composed of triangular grids, and model B with rectangular grid. So we examine pros and cons each. So in model A, it is very stable and good shape, but it is very hard to move it. But in the case of model B, this is very flexible and unstable, but it has merit about to move easily. So I selected this model B for mock-up test. So this is the photos for unfolding procedure. First, we bring these scissors on the place and try to unfold. So this is an open shape, and we attach the entrance and window and skins like this. So final shape is like this. So let me show you the video for the deployable shelter system. So you can see just 5 person working. So also you can check this time. Please guess how long time it can be built. So in more detail, it has 5.6 meter of radius and 2.8 meter of height. So it has enough space for people. So now they are attaching membrane with bolt inside of the Ligeras system. When during winter, you can use additional membrane outside of the shelter. So now time is 22 minutes, and they are working for finishing. $27, $28, $29. Okay, we finished. It takes just 30 minutes with 5 persons to build our evacuation shelter. So this is inside the view, relatively enough space. Also, this is about a variety of design. This is the fundamental model, but we can apply this fundamental model to 2-bay model or 3-bay model. Also, we can connect in the cross direction continuously like this. Next example is deployable facade. So we have many kinds of serious members like this to make a variety of shape like this. So this is an example for facade. So this is an open shape and this is a closed shape. And we can combine these two to make a beautiful facade like this. This is an example for the facade attached to a building outside for interior and exterior function and for energy performance. Next item is dynamic instability. Usually dynamic instability is very difficult, so we need more time to understand. But today I'll show a very interesting figures. We have 2 basic behavior after a critical point. This is this show a stable behavior after critical point, and this is unstable after a critical point. Usually, olivocline is on the this scope, but shell-like structure shows usually this phenomena. So this is very sensitive to initial condition with very strong nonlinearity. So usually a shell-like structure has two kinds of instability. One is a direct snapping, which is a kind of snap-through in static analysis. And the other is indirect snapping, which is a kind of bifurcation. So in the direct snapping, just symmetric modes are combined to make a jumping like this. But in indirect snapping, symmetric modes and anti-symmetric modes are combined to make jumping like this. This is a kind of a coupling. So this is very sensitive to initial imperfection. So I introduce result of EP shells. So this is the static buckling loads. So here, lambda S is a kind of shell parameter which represents shell shape. It includes large span ratio and thickness and so on. So lambda becomes a lower number. It means a very shallow shape. And lambda becomes a higher number. It means a very deep shell. So in this result, we can see lambda is less than 3. We don't have any snapping like this. And between 3 to 7 over 8, it shows snap through. And higher than 8, it shows bifurcation. So this is a result of a dynamic buckling load. So in this figure, 1 means snap through buckling load in static analysis. So these are dynamic buckling loads. So this is for direct snapping. This is for indirect snapping. So in the case of direct snapping, it shows about almost 80% of snap through buckling. And in the case of indirect snapping, it becomes almost 50%. So this is very, very important and very serious in structural design. So we have to check always about this nonlinear instability. So this is a very interesting figure to explain the dynamic instability about running spectral analysis. Here, these figures for lambda equal 5, it means a very shallow shape. And next page is a lambda equal 11. It is a very deep shell. So in the case of shallow, as a direct snapping model, this is a first mode, which is a symmetric mode. And this is a result of a second mode, which is anti-symmetric mode. So first mode component is moving like this, and the second mode moving like this. So interesting thing is you can find that another component like this. So this strange component coming out and going through this line and meet the second mode to make instability. And you can find this component started with almost half of first mode. In the case of indirect snapping, this is first mode alone, and this is a second mode. Also, you can see the strange another component. So this strange component is almost half of first mode. So usually indirect usually in dynamic instability, you can say direct snapping is a super harmonic resonance, and indirect snapping shows a subharmonic resonance. So this is a very important concept in indirect dynamic instability. To examine furthermore the characteristics, I will show you the result of arch. So this is time history curves. So left side is a free buckling load, and this is right side is a force buckling load. So here is H equals 3. This is H equals 5. This is H equals 7. H means a kind of rise spin ratio. So H equals 3 is for direct snapping model, and H is higher than 5. It means indirect snapping model. So in this case, the vibrating is like this, and show just a general nonlinear dynamics curve. But here, in the case of indirect snapping, you can see a very interesting phenomena around here. So that at the beginning, the first mode, which is a symmetric mode, is vibrating very tiny. And then the second mode of anti-symmetric mode is coming out around here and interfere the first mode. And then first mode is going to another vibrating. So it is a kind of divergence. So I can show these figures on the phase curve. So this is displacement, and this is velocity. So in the case of direct snapping, the vibrating is moving this orbit, so which shows closed form like a water drop. But in the case of indirect snapping, first time this moving around here, and interfered by second mode, it moving another space. So it is not going to back to the original point. So this is a kind of chaotic phenomenon. So this is very, very important, and we have to check this phenomena furthermore in the future. Thank you.
Professor Kim, thank you very much for taking us through your presentation there. A very interesting overview of a number of topics, including deployable structures, among others. Very, very interesting. Thank you for providing that for us. We're now going to move on to the final section of our interview, which looks to the future of spatial structures, and in particular, the forthcoming 2021 conference. A key theme of the Spatial Structures 2021 conference is inspiring the next generation. What advice would you offer, Professor, to aspiring engineers looking to enter the field of spatial structures?
First I like to say welcome to the new world, to the next generation. Currently, most of the buildings are built by very general technology with general materials such as concrete and steel. However, spatial structures are very different compared to general buildings. And that's why it's very exciting field. Spatial structure field can always confront a variety of new materials and new structure systems. The cycle for advancing the system happens so rapidly with new technology and research, especially if you change the shape of a structure. You can improve on not only the outer design, but also the strength too. And this can open the gates of new world of architecture. The future is waiting for you, and I know it could be harder to adapt the new system because you might as well have to go outside of box, but welcome to the field of spatial structures.
Thank you, Professor. And I think a number of the topics you've touched on there will be key themes at the 2021 conference. So we look forward to the opportunity to debate them there, hopefully with guests such as yourself. In terms of challenges in the field, we've touched on a few there, but what do you think are the most pressing challenges in the field of spatial structures with respect to the current global challenges?
Yeah, we have currently facing with lots of global challenges, which includes global warming, limited resources, environmental and corporate sustainability, human sources, COVID-19, and more. In spatial structure, the most pressing challenge is related to the limited resource, such as non-reusable resources. To build the new structure, we will require materials, but with the limited resources, we need to test a new type of material for future structures. Furthermore, this solution can be linked with limited energy because after building a structure, it will require energy to operate. But with the limited resource of energy, we are facing the global challenges. We need to work together to solve the challenges that we are facing at the time, not only with the field of spatial structures, but also with environmental science, material science, mechanical engineering, and so on. This is, I think, everyone's lifetime homework.
A very good point, Professor Kim. Thank you very much for your answers and indeed for your presentation today. We've reached the end of our interview, but it was a pleasure speaking to you on the Movers and Shakers interview series, Professor Kim. And hopefully, as we move closer to the IASS 2021 conference, we can catch up with you again. But for now, Professor, all the best. And thank you once again for your time today.
Thank you very much, Mark.
Thank you, and speak to you soon.